So during the first week, we looked at a guy swinging a golf club, and we looked at it through the kinematics lens. But this time, we're going to look at it through the energy lens. So we went to the golf course and filmed Marcus hitting a golf ball. So we then took that video and put it into Tracker and found the velocities, and then we used that to calculate the kinetic energy, and later on the work Marcus put on the ball. So after that, later way on, we're going to talk about conservation of energy as well.
After we uploaded the video onto Tracker, we used the golf club, which is about 1 meter, as our measuring stick. We then tracked Marcus's swing, and after we switched to the velocity graph, we could see a couple key points. The top of the first curve is the velocity of his backswing. The point where it hits 0 is when he hits the top right before his forward swing. Then he maxes out at about 10 meters per second before he hits the ball, then falls to an average of about 8 meters per second.
So as we just found from Tracker, we found the velocity of the club to be 10 meters per second, and we measured the mass of the club to be 0.45 kilograms. So now we can take those two values and put them into the kinetic energy equation, which is kinetic energy equals 1/2 times the mass times the velocity squared. So putting those in, we can find kinetic energy equals 1/2 times 0.45 kilograms times 10 meters per second squared. And that ends up being 22.5 joules. So now, if we pay attention to units here, we can see that kilograms times the meters per second squared is ultimately kilogram meters per second squared, which is joules.
We repeat this process, but this time we're going to track the ball. Again, we use our golf club as our measuring stick, which is about 1 meter, and we track the ball along its parabolic movement. We're going to go until it hits the ground, as that's the best way to measure the velocity that Marcus actually gives the ball, and therefore we can calculate the kinetic energy of the ball. When we look at the velocity graph, we see that it's about between 6 to 8. For our measurements, we're going to use 8 meters per second.
Alright, so from Tracker, we found that the velocity of the ball is 8 meters per second, and we looked up the standard mass of a golf ball, and it turns out to be 0.045 kilograms. So using these two things, you can plug them into the kinetic energy equation. Make sure that you don't forget your units. And when you plug this in, you'll get 1.44 joules. And he already told you how that works out. Alright, so to find the work done on the ball, work is the change in energy. And to find it, we look at the final kinetic energy of the ball minus the initial kinetic energy of the ball. And since the ball is at rest, this is actually 0. So the change in energy, or the work done on the ball, is just equivalent to this right here.
So therefore, we can take the kinetic energy initial of the system equal to the kinetic energy final of the system. Now, the kinetic energy of the system initial is equal to the kinetic energy of Marcus initial plus the kinetic energy of the ball initial equal to, now for the kinetic energy final, we can take the kinetic energy of Marcus final plus the kinetic energy of the ball final plus heat, since we have some energy lost to heat. Now, we have two unknowns, heat and kinetic energy of Marcus final. So for the kinetic energy of Marcus final, we can use 1/2 mv squared, and we substitute in 1/2. The mass was 0.45 kilograms times our velocity, which was 8 meters per second squared, and we get 14.4 joules. So now we take all our values and plug it into this equation. So for our kinetic energy of Marcus initial, we have 22 joules, plus the kinetic energy of the ball initial, which is 0 because we start from rest, is equal to the kinetic energy of Marcus final, which is 14.4 joules, plus the kinetic energy of the ball final, which was 1.44 joules, plus our own unknown heat. So when we calculate for the unknown, we get 6.66 joules.